Following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. Alrighty, today we're going to go on and cover section 11.4. While I'm thinking about it, just a reminder, Monday there's no class. It's a holiday. Okay. Anyway, let's take a look at a scenario. We've been talking about exponential equations. Let's say we had the following. 2 cubed equals 8. And then we had 2 to the 4th power equals 16. Okay. What if we had 2 to some power x equals, let's say, 10? What do we know? Well, we could look and see that x must be somewhere between 3 and 4. And I suppose through trial and error, we could go 2 raised to the 3.1 power, 2 raised to the 3.2 power. And after a while, we could get however accurate we wanted to get an answer, but that's not a real efficient way of doing things. So let's take a look at this again. 2 to the x equals 10. What we need to do is we need to isolate that x so that we can solve for it. There's a way of doing that. If we have an exponential equation in this form, we can rewrite it in a form that's called a logarithmic equation. And the logarithmic equivalent of 2 to the x equals 10 would be log base 2 of 10 equals x. So let's put a double arrow there. Okay, those are equivalent statements. The equation on the left is an exponential equation. The equation on the right is called a logarithmic equation. Now, on the left, we have a base of 2 raised to the power x equals 10. On the right, the way we describe that is we would say log base 2 of 10 equals x. What I want to point out is, in both cases, the 2 is referred to as the base. Okay, I like to talk about inning of baseball. You've got 2 teams, one up to bat, one out in the field. And out in the field, there's the diamond, there's home plate, first, second, and third base. Okay, after the team up to bat makes 3 outs, the players change places, but the bases stay out in the field. So the players change places, but the bases stay the same. So looking at this, the base stays the same, but here the 10 and the x trade places. But be careful, this is 2 to the x power. This is not 2 to the 10th power. They're connected, but it's not connected as 2 to the 10th power. It's log base 2 of 10. But anyway, the bases stay the same and the players, the other 2 numbers, change places. That's just a little thing that I use to remember that. What we're going to do now is we're going to practice this idea of changing a logarithmic equation into an exponential equation, and then changing an exponential equation into a logarithmic equation. Why practice that? Well, the reality of it is, most of the time when you're dealing with a logarithmic equation and you have to solve it, you end up changing it to an exponential equation. And most of the time when you're solving an exponential equation, you change it to a logarithmic equation to solve it. So this is an important piece of information to know. All right, we have the following. Log base 3 of 81 equals 4. So the base is 3 and the players change places. So 3 to the 4th power equals 81 would be the equivalent exponential equation. All right. Here's another one. Log base 10 of 100 equals 2. The equivalent exponential equation would be 10 squared equals 100. So basically, what is a log anyway? Well, let's go the other direction. A log is an exponent, isn't it? Because the log of this gives us this exponent. The log of this gives us that exponent. All right, more examples. Log base 6 of 1/36 equals -2. So writing that as an exponential equation, we would have 6 to the negative 2 power equals 1 over 36. Log base 8 of the cube root of 8 equals 1/3. Changing that to an exponential equation, we'd have 8 to the 1/3 power equals the cube root of 8. Isn't that true? An index of 3 is like an exponent of 1/3. Okay. Here's another one. Log of 0.01 equals negative 2. Well, wait a minute. They didn't write the base for the log. So let's talk about some special notation, and then we'll come back to this problem. All right. Log base 10 is used very frequently in mathematics, so frequently that it's referred to as common log. Okay. Mathematicians like to use shortcut notation, so when something's used a lot, they tend to have a shortcut thing. For instance, if you take the cube root of 8, they put a 3 in there for the index. But if you take the square root, they don't bother putting a 2 in there because the square root is the most popular root. So what does that mean here? Well, since log base 10 is a very popular base, they will just write log base 10 as log. And the good news is on your scientific calculator, typically over on the left column, there is a button that says log, which is log base 10. And if you forget what base it is, the second function key above that is 10 to the x. So there's the clue that, oh, log is log base 10. All right, so let's go back to this problem. I'm going to use red to write in what's assumed as there but not written there. Okay, so now changing this into exponential form, we would have 10 to the negative 2 power equals 0.01. All righty. Let's see here. X equals log base 9 of 81. So that would be 9 to the x power equals 81. They're not asking us to solve for x yet. They're just asking us to change from one form to the other. And finally, log base m of p equals 101. So m to the 101 power equals p. So there's examples of changing from logarithmic equation form to exponential equation form. Now let's go the other direction. Let's take a look at some examples of exponential equations and change them into logarithmic equations. Let's see here. 10 cubed equals 1,000. So this would be log base 10 of 1,000 equals 3. Note we could have also written log of 1,000 equals 3 because the 10 would be implied. Okay. 3 to the negative 4 power equals 1 over 81 becomes log base 3 of 1 over 81 equals negative 4. Let's see here. 1/3 to the negative 3 power equals 27. Log base 1/3 of 27 equals negative 3. How about m to the n power equals p? Log base m of p equals n. In each case, the base is the same. The other two numbers switch places. Okay, in this one, 12 to the negative 2.6 power equals n plus 1. So this would be log base 12 of n plus 1 equals negative 2.6. But it's important that I group the n plus 1, because otherwise, without those parentheses, it looks like the log base 12 of n plus 1. But all of this has to be quantified there. So be careful with your grouping symbols. Okay, now we're going to solve some equations. And this says log base x of 9 equals 2. As I mentioned before, If we're solving a logarithmic equation, typically we change it to an exponential equation and vice versa. So let's write this in exponential equation form. It would be x squared equals 9. All right. Well, to solve this equation, we could use what the square root property. Take the square root of both sides and get x equals plus or minus 3. However, there's a problem with these answers. Let's go back to looking at exponential equations and domain and range and all of that. Let's say we've got y equals b to the x power. Okay, this goes back a day or two ago. We said that b had to be greater than 0 and b couldn't equal 1. X, the domain would be what? All real numbers. And y, the range would be greater than 0. Okay, so the base has to be positive but not equal to 1. The exponent can be any real number, and the constant over on the left has to be greater than or equal to 0, or excuse me, greater than 0. Okay, so now if we take this and we rewrite it in log form, it looks like that. But keep in mind, this b is the same b. This x is the same x. This y is the same y. So since b has to be greater than 0 and not equal to 1, that means that the base has to be greater than 0 and not equal to 1. Therefore, x equals 3 is the only valid solution. So yes, -3 is a solution to that equation, but in the context of this problem, we have to toss out the -3 answer because again, the base has to be greater than 0 and not equal to 1. Okay, let's see here. Log base 7 of x equals 0. Writing that as an exponential equation, 7 to the 0 power equals x. Well, 7 to the 0 power equals 1. So log base 7 of 1 equals 0. Let's see here. Log base 4 of 16 equals x. Solving that, we get 4 to the x power equals 16. Well, because logarithmic equations and exponential equations are both one-to-one functions, I hadn't mentioned that logarithmic equations were one-to-one functions, but because both of them are, if we can write this exponential equation so that the bases are the same on both sides of the equation, we can then assume the exponents are the same. So for instance, I could take 16 on the right side and write it as 4 squared. Well, 4 to the x power equals 4 to the 2 power. Therefore, x equals 2. Okay, let's see here. How about this one? Log base 27 of x equals -1/3. Changing this to an exponential equation, 27 to the -1/3 equals x. Well, let's see, 27 to the -1/3 would be 1 over 27 to the +1/3, which would be the cube root of 27, which is 3. So x equals 1/3. And let's see here. Log base x of 0.001 equals -3. Changing that to an exponential equation, we get x to the -3 power equals 0.001. Well, not only can we have a situation where if the bases are equal, then the exponents have to be equal, but if the exponents are equal, in this case, the bases would have to be equal. So how could I get that? Well, okay. The exponent on the left side is -3. If I take 0.01, I could write it as 10 to the -3 power. Think about scientific notation. So x equals 10. Okay, so log base 10 of 0.001 equals -3. because 10 to the negative 3 power equals 0.001. And note, you could also write that as log of that because 10 is implied when it just says log. Okay, now this says evaluate each logarithmic expression. Log base 3 of 9. It doesn't say this, but it means do it without a calculator. I don't know what that's equal to, so let's call it box. We'll say log base 3 of 9 equals box. Well, what if we took that, which is now a logarithmic equation, and wrote it in exponential form? Wouldn't it look like that? And then couldn't we take the right side and rewrite it like that? So now the box equals 2. So log base 3 of 9 equals 2 because 3 squared equals 9. Let's see here. Log 100,000. Well, we'll just say that equals box. Don't forget there's an implied 10 there. So changing this to exponential form, 10 to the box power equals 100,000. 100,000 is 10 to the what? 1, 2, 3, 4, 5th power. So the box equals 5. So log of 100,000 equals 5. I mentioned your calculator earlier. On your calculator, the log button, if you just push that log button, you get log and then parentheses, put in 100,000, close it up with a right-hand parentheses, push equals, and you should get 5. Okay. Now we're going to use our calculator to find the log of 0.57. So again, this is log base 10. So on my calculator, I'm going to push the log button. A left-hand parenthesis shows up 0.57. Close it up with a right-hand parentheses, push equals. They said to give answer to 4 decimal places. Negative 0.244125, etc. There's your 4th decimal place, the 2 rounds down. So negative 0.2241. Okay. How about the log of 375.876? So again, we'll push log. And when we do, a left-hand parenthesis comes up. Put that inside, close it up, and push equals 375.876, close it up. And I'm getting 2.57504. The 4 would round down, so 2.5750, taking it out 4 decimal places. Okay. Now, we're going to use the calculator to solve an equation. This says log of x equals 2.8945. Don't forget there's an implied 10 there. So I could rewrite that equation as 10 to the 2.8945 power equals x. Now, where am I going to access 10 on my calculator and raise it to a power? There's a couple of different ways. I can just put in a normal 10, and then I can use the little caret key, and then put in the exponent 2.8945, and I get the answer, 784.3321. Or I can use the second function of the LOG button. Don't forget, so LOG, and then up here we have a 10 to the x. So I could go second, push the LOG button, and this shows up like that all at once, and then put in the, let's see here, 2.8945, close it up, and you get the same answer. So you can access 10 to the x by using 10 and raise it to the caret little thing parentheses, or you can use the second function key of log, which is 10 to the x. Both of them work. Okay, let's take a look at some application problems. This says stocking lakes, not as in stalking someone and not as in stockings you put on your feet, but as in putting fish in the lake, stocking lakes. It says a farmer stocked a lake on her property with 75 sunfish. She was told that with a proper oversight, the sunfish population could be approximated by the logarithmic function f of t equals 75 plus 45 times the log of t plus 1, where t is the number of years since the lake was stocked. Find the number of sunfish she can expect in the lake in 2.5 years. So time is 2.5 years. Let's change that to 2.5 years. So we want to find f of 2.5, which is going to be 75 plus 45 times the log of 2.5 plus 1, which is 75 plus 45 times the log of 3.5. So now on the calculator, 75 plus 45 times the log of 3.5, close it up, and let's see here, I get 99.48. So rounding to the nearest fish, it would be about 99 sunfish. Okay, let's take a look at another problem. It says children's height. The logarithmic function h of a equals 29 plus 48.8 log of a plus 1 gives the percent of the adult height of a male child a years old has attained. If a boy is 9 years old, what percent of his adult height will he have reached? So basically, we're trying to find h of 9, which would be 29 plus 48.8 log of 9 plus 1, which would be 29 plus 48.8 log of 10. So on the calculator, 29 plus 48.8 log of 10, and I'm getting 77.8, so that would be 77.8%. Alrighty. Well, that's all I've got for you today. So have a good weekend. I'll be back at 1:15 this afternoon. Keep in mind, Monday is a holiday, so no class on Monday. I'll be back Tuesday morning. And anyway, have a great, safe weekend. And I will see you next week, perhaps.